Welcome back, AP 11.3. We're going to talk about three properties of liquids. One is called viscosity, surface tension, and capillary action. Viscosity, the resistance for a liquid to flow. And the reason why is because of intermolecular forces. So like examples of liquids that you come in contact with that like flow very slowly are like syrup, molasses, honey, ketchup, okay? Any of those things. My son the other day was trying to get conditioner out of the bottle and it just wasn't flowing out. That's viscosity. So what happens is the liquid flows by sliding over molecules. Like I always like to think of it like those ball pits when you were a little kid, you would play in, you would jump in, and then it's kind of like it was really hard to move from one side to the other because you had to kind of like swim through the ball pits to get to the other side. So if you want something to flow faster or make it even harder to flow out of that container, what can you do? So the greater the liquid's viscosity, the more slowly it flows. So when you have high viscosity, I'm just going to call it Viz, okay? High viscosity, that means it's flowing very slowly. You can measure it, viscosity, by timing it, how long it takes for the liquid to flow out of the bottle. The slower the flow, the higher the viscosity. Viscosity also depends on attractive forces, aka intermolecular forces. The stronger the forces, the higher the viscosity. Okay, so really strong forces have high viscosity. And why is this? Because molecules are more strongly attracted to each other and it prevents them from flowing around each other. So when you have very strong, especially London dispersion forces, it prevents them from flowing faster. What about electrons? We don't like to say molecular weight, but it's about electrons. Viscosity also increases with the number of electrons, aka weight. The larger the molecule, the higher the viscosity. And what happens is it's the electrons. They get all tangled up because when you have a lot of electrons. I like to think of it like pasta, like spaghetti. When you have cooking spaghetti and it gets all tangled up and then you're rinsing it off and then you try to separate it, it gets all tangled up from one strand to the other. So the larger the molecule, the more tangled it gets, the more electrons. So be very careful when you're talking about mass, because remember, mass is protons and neutrons. We're talking about the electrons are getting tangled up. But if you want something to flow faster, so if I want to flow faster, well then crank up the temperature, okay? What happens is viscosity gets weaker when you increase the temperature. At higher temperatures, you are gaining kinetic energy, and the molecules are gaining this energy, which means they can actually move faster and more, okay? Because you're overcoming those forces between the molecule. I always like to give the example like cold oil versus hot oil. If you've ever put oil in a pan and you heat it up, oil has high viscosity. But when you actually heat the oil up, you actually decrease your viscosity. It actually flows faster because you have overcome intermolecular forces. Okay, you're kind of breaking them apart to get those molecules untangled. So that's how viscosity can change with either temperature, intermolecular forces, and electrons. Surface tension. All right, surface tension. Sorry for the four-legged animal in the background. Surface tension is the measure of the inward force that must be overcome to expand the surface area of the liquid. So we looked at surface area in the video right before this in 11.2, okay? The surface area of water behaves almost like it has like this thick skin. And as evidence, when you actually see like some insects that walk on water, because of that thick skin, those high intermolecular forces, aka hydrogen bonding, some insects can actually stay on top of the water, which means they didn't break the surface of the water. They didn't sink down to the bottom. We go into the water, we definitely have broken the surface tension of the water. So in the figure below, let me show you the picture with the insect. Molecules in the interior are attracted equally in all directions, but those at the surface are only attracted to the inward. Let me show you what we mean by that. So if you blow up the water microscopically, at the surface, these molecules are only attracted inward. So on the surface, there is no upward force, okay, to cancel out the downward force. So which means each surface molecule feels this downward pull. So they're only experiencing the attraction for anything below it. But then you get these molecules down below in the surface, okay? They're actually feeling force in every direction. Up, down, left, right, every direction. So they feel no net pull in any direction. Only the surface is feeling this downward pull to break the surface. So this net force tends to pull surface molecules towards the interior, therefore reducing the surface area, making the molecules at the surface pack closely together. So you actually, if you notice the picture, in the molecules at the top, okay, the molecules are actually closer together on the surface. Compared to, look down here, you actually have more space between the molecules. Okay, because it's below the surface. Because spheres have the smallest surface area for volume, water droplets usually have a spherical shape. Okay, you can see this a lot on anything that has to do with water versus a nonpolar substance. So let me give you an example of that. You tend to see water, it's called beating up, when it comes into contact with the surface that's nonpolar. Think of like a leaf. A leaf is nonpolar because it has like this waxy type of feel on the outside. Tomatoes also, every time they put tomatoes in the store, they coat them with this wax type of surface to make tomatoes look more attractive when you want to buy the certain color of tomatoes. Apples, same thing. You have to kind of clean off that wax to get to below the surface. Anytime you've ever waxed your car, what you see on your car, and if this is a wax surface, that water drop hits it and it creates this dome-like shape. It's because of polar versus non-polar. Can I break the surface of water to make it flat? Yes, I can. So you usually have to add something to break the surface, and usually it's soap, okay? So if I want to take that same wax surface and add like a finger, and we'll do this demonstration in class, like a finger with soap on it, okay, you can actually break the surface of water and then it's flat, okay? We call it a surfactant, okay? It's a chemical that's added to break the surface tension of whatever that chemical is. And a lot of time, that's why we add soap to clean our dishes, to clean our clothes, to clean the car, is because soap can break the surface tension of fats and oils and water. It's pretty impressive. If you have something that has high surface area, it means you have high intermolecular forces, aka like water. Okay, water has very high surface area because of its strong intermolecular forces. Molecules are attracted to each other more. So a molecule in the interior of the liquid is attracted to the molecule surrounding it, whereas the molecule only at the surface of the liquid is only attracted to what's below it. Okay, so if you have very strong forces, they are very attracted to each other. So trying to break through that surface is going to be really tough. Stronger intermolecular forces causes to have stronger surface tension. Water has actually one of the highest surface tensions out of any chemicals because of its strong hydrogen bonds. If it was something like oils and sugars, like C12O6, C12H12, oh my, blah, blah, C6H12O6, which is sugar, nonpolar, okay, basically you would have very low surface tension because you have very weak intermolecular forces, okay? Capillary action, I know you heard this probably very briefly in biology, but cohesive and adhesive. Capillary action is the ability for a liquid to rise up a tube, okay? So if I have a liquid that's in a tube and I'm trying to make it rise up a very narrow tube, we actually have what's called capillaries in our stockroom. I'll show you what they are. They're like the tiniest tubes like you've ever seen, probably as thick as like a needle, okay? They're very, very thin. And if I'm trying to get the liquid to go against gravity, well, I have to talk about two forces that either bend the molecules a certain way or bend them in a different way. So we got some vocab here. Cohesive, okay, means that, let's blow up the picture kind of, make it a little bit wider, okay? The intermolecular forces that bind molecules to one another, okay? So most liquids, like water, they have this U-shaped type of what's called meniscus. Okay, so like I said, like water, okay, most liquids do. Cohesive are the molecules that bind one molecule to another. So like this molecule versus that molecule and that molecule, they're very close together. So that's the cohesive that we're talking about. That attraction between this one or this one or that one or that one, that attraction. Adhesive are the molecules that bind molecules to the surface of the tube. So water bends towards the side of the container because of these forces. So we're talking about this part right there. So those molecules that are sitting right there near the surface and the edge of the container, those forces are the adhesive forces. So is it on the side of the tube or is it the molecules within each other? So let me show you the difference between the two. The meniscus in a tube has a shape. Okay, and we're used to water having this U type of shape. We've seen it every time we look at a graduated cylinder. You don't really see it at home too much unless you have like a really thin vase or a glass that's really, really narrow. If, okay, you have two scenarios. Okay, so this is for water. Adhesive, if it's greater than the cohesive. Okay, so if your forces are stronger for the adhesive versus cohesive, you have a U-shaped curve. So the adhesive, remember, those are the molecules that bind to the surface and the container more than the molecules themselves. So that's why you have this U shape. But what about mercury? Mercury is actually different, okay, a metallic liquid. Mercury atoms can form bonds with one another, but not with the glass. So in this case, you actually get your cohesive. Remember, these are the ones that bind molecules to each other. You actually have stronger forces with the molecules binding with each other, so you get a downward curve like you see in this picture right here, okay? So we don't have mercury for us to actually show you or anything like that. But I wish we did. We have to rely on Google pictures and videos. But this is what we're used to right here. So in case of our water, our adhesive forces are greater than our cohesive. And for mercury, our cohesive is greater than our adhesive. So if you know the shape of the liquid, then you know how it bends. And then you know which forces are stronger than the other. Okay? But water, and I'm going to put and most liquids. Okay? There's no liquids that are flat. They have a meniscus. The question is that an upward meniscus or a downward meniscus? Okay? Now give it a thought. What we've talked about so far with viscosity and surface tension. Okay? How can temperature increase and affect viscosity and surface tension? Okay? So, as temperature increases, okay, the viscosity, remember what viscosity was about, the resistance to flow. The viscosity decreases because the average kinetic energy increases, which causes the molecules to move more. And breaks attraction. Remember, we're not breaking bonds. We're breaking attraction between molecules. Okay, so that's how temperature can affect viscosity. What about surface tension? Okay, so with surface tension, as you increase temperature, okay, surface tension actually decreases. Okay, and I don't mind in your notes if you use the up and down arrows, that's fine. Because, remember, you're cranking up the temperature, so what else is changing? So my kinetic energy is increasing, and it causes them, same thing, the molecules to move faster. And it weakens the intermolecular forces. And more specifically, which one is it weakening? It's weakening the LDF force. Remember that initial attraction between them. Okay? How does viscosity and surface tension change with intermolecular forces? Okay? So as intermolecular forces become stronger, so we're talking about LDF, dipole, and hydrogen bond type of molecules, the viscosity increases since the molecules are strongly attracted to each other. You have very strong forces, okay? That means viscosity is really, really high. So instead of increase, we'll say very high, because the molecules are very strongly attracted to each other and they're very close to each other. So it makes it hard to break them apart. As the intermolecular attraction becomes stronger, so as the intermolecular forces attraction gets stronger, your surface tension is stronger. Remember, the highest intermolecular forces, hydrogen bonds, if they're strong, you have a high surface tension. And the reason why is the same thing, due to the molecules strongly attracted to each other. The closer the molecules are, the harder it is to break them apart. And which forces are the hardest to break? And it's hydrogen bonds. Okay? Hopefully you did okay with these three topics: viscosity, surface tension, capillary action. So I'll see you on the next one.